In the previous lecture, we defined for ourselves the notion of controllability. We also saw how we check for controllability via the rank condition of the controllability matrix. We also saw what happens when the system is uncontrollable. What we saw was when the system is uncontrollable, there is a pole zero cancellation, that the uncontrollable pole gets cancelled by a zero, which means I am unable to control that pole. And the transfer function therefore has only those poles, or the transfer function shows me only those poles. The transfer function carries information of only those poles which are controllable. Okay, so what can we do with the systems that are controllable? So, in this lecture number 3 of week 11, we will talk about pole placement. Okay, so what do we know about poles? So, poles, if I talk in a state space notation or state space notion of x dot is Ax plus Bu. So, poles will also be the eigenvalues of A, and we know a lot about poles, right. So, poles determine stability. If the original system is unstable, say I have a system of the form x dot equal to x plus u, if I have a u which is equal to say minus 3x, so x dot will become x minus 3x, this is minus 2x. So, original system was x dot equal to x, which was unstable. Now, I am at a system where x dot is minus 2x, which is stable. Okay, so if the original system is unstable, poles can be placed at appropriate locations, right. So, I can place not just at minus 2, if I want the pole at say minus 5, I just use u equal to minus 6x, resulting in x dot equal to negative of 5x with the pole at minus 5. So, what do poles do? So, location of poles have immediate impact on the transient response. Systems closer to the origin will closer to the imaginary axis will have a faster response. They will also have a larger overshoot, but these are also susceptible in the sense of a small change in parameter can push it to the unstable region. Okay. So, here in the second order design, we just looked at placing poles at appropriate location to have certain specifications on the zeta and settling time, which resulted in certain design of zeta and omega n, and therefore the dominant poles. Okay, so location of poles therefore directly impact the settling time, the overshoots, and they also look at if the system is oscillatory or it is non-oscillatory and so on. Location also of the poles also decide the ability to reject disturbances. We won't explicitly do this, but we will implicitly check what these things mean. So, the question that we will try to answer in this lecture is, can we design an appropriate control law which will place the poles at the desired location, and this will be this technique will be called pole placement. Okay, so what did we look at last time? So, we saw that the following statements were equivalent, that if a n dimensional pair AB is controllable, the controllability matrix has a full rank. So, these are also called the Kalman rank conditions. Okay. And when the rank is less than n, the system loses controllability, which results in or which shows up as a pole zero cancellation of the uncontrollable pole, and therefore, whatever I can if I have a transfer function of the form x square plus s plus 1, I can only control these poles, right? I cannot control the uncontrollable ones. So, what shows up in the transfer function are only the controllable part, and therefore, controllability is a necessary condition for pole placement. And what we also concluded or saw with help of examples was that the transfer function of the system is transfer function of only the controllable part. Okay, so how do we change the location of these eigenvalues or even poles? And if you can change, how do we put those poles and where do we put those poles? So, during this discussion we will assume that the system is completely controllable, that there are no pole zero cancellations and so on, and the state variables are measurable and are available for feedback, and lastly that the control input is unconstrained. So, I do not really bound the input with some number. Okay, so the classical approach is translate your design specifications into locations of dominant poles, which will be roots of this characteristic equation. Then place the rest of the poles so that they are much faster. So, if this is my dominant poles, place the remaining poles so that their effect dies down pretty soon, and what happens, what dominates the analysis is only the dominant pole. Okay. So, what happens in this current approach is we would like to place all the poles at desired locations, right. So, and we see how it is kind of very straightforward to do this, and we do not necessarily need to stick to the dominant pole analysis. Okay. So, the only difference from the classical approach is all poles are forced, or they can be made to sit at desired locations, and the necessary and sufficient condition is that the system is completely controllable. We have seen why this is necessary from this little argument. We will slowly see why these conditions are also sufficient. Okay, so we start with a system x dot is ax plus bu. I do not really need to know what is happening with the output, because I assume that all my x all my states are available for measurement, and a typical control law will be of the form u equal to minus kx. So, I have x dot equal to ax plus bu, b and u is now negative of kx, resulting in now a closed loop system of the form x dot equal to a minus bk times x. So, what are the poles of the open loop system? These are typically the eigenvalues of A. What are the poles of the closed loop system? These are now eigenvalues of A minus B k. So, if eigenvalues of A are not satisfactory, the question here is, okay, so this is the these are the eigenvalues of the closed loop system. Of course, A is given, B is given, only a change that I can make is k. So, can one design an appropriate k such that the closed loop poles are at desired locations, say some mu1 till mu n. Okay. So, now this is how my closed loop dynamics looks like. The objective is to find a k such that the closed loop poles, which are obtained by solving this characteristic equation, are at this desired pole locations, right. So, start from maybe these poles are at some p1 till pm, change this p1 till pn to mu1 till mu n. Okay, so first is check for controllability, because if I were to control all the states must be controllable. So, if I say I have a system of the form x1 dot, x2 dot is 1 0 0 2, x1, x2, plus 0 1 times u. So, with u equal to whatever, say k1, k2, x1, x2. So, this is the standard form u equal to kx with a negative. I can only do let us say k is 1 comma 1, right. So, u equal to minus x1 minus x2, x1 dot still remains 0, x2 dot will be minus 2 x2, sorry, plus 2 x2, okay, let me say this is minus 5 x1 minus 5 x2. Okay. So, x1 dot still remains 2, x2 dot now becomes 2 x2 minus 5 x1 minus 5 x2. So, this is minus 5 x1 minus 3 x2. Okay. So, I will have a closed loop system now of the form 1 0 minus 5 minus 3. Okay. Is it stable? No, because I still cannot do anything with this eigenvalue, right. So, in this case, so first check for state controllability. Here the controllability matrix is, so B is 0 1, A times B is 1 times 0, 0 times 1 is 0, so this is 2, right. So, this rank here of this controllability matrix is 1, which is less than 2. The system is not controllable, and therefore controllability is a necessary condition. Okay. So, assume that the system is controllable, what happens then, right. So, my k will be of this form k1, k2, k3, this is k1, k2. So, on the left I will have a polynomial in S with unknowns, say k1, k2, k3. Okay. On the right I will have, so I can also write this as s power n plus alpha 1 s n minus 1 and so on till alpha n, or whatever is alpha n minus whatever this will be the index of s power 0. Okay. So, here on the right I will have, so because these mu's, mu1, all these mu's are known, alpha 1's, the alpha i's are also known. Okay. So, if I give a expression of the form s square plus k1 s plus k2 is s square plus 2s plus 1, then we can easily equate the coefficients and say that k1 is 2, k2 is 1, right. So, this is precisely the method 1 that we are talking of. So, on the right I have a polynomial of which all the coefficients are known. On the left I have a polynomial which has some unknown coefficients, which is where the control law needs to be designed. I just equate and I get my desired equation. So, suppose I start with a system of this form where pole locations are at minus 1, minus 2 and minus 3. Let us say that I want the desired poles not at minus 1, minus 2, minus 3, but say 2 poles are at minus 2. Okay. So, Si minus A minus Bk. So, this is the equations in the unknowns. Okay. Where does this come from? This comes from S minus this is this s plus 1, s plus 2, s plus 2, right. So, this is the known part. So, this is my s minus mu 1 times s minus mu 2, s minus mu 3, right, as in this this expression here. So, things on the right hand side are known to me. So, I can expand this to get something like this. Left hand side I do not know things. So, now what I do, I equate 6 plus k1 equal to 5. So, k1 is minus 1. Similarly, 11 plus k2 coefficient of s 11 plus K2 is 8, K2 is negative of 3. Lastly, this 6 plus K3 is 4 and K3 is minus 2. Right? That's the simplest of all pole placement methods. We are just equating the two characteristic equations, right? And of course, for lowered order systems, I can do this. What if n is 7 or 8? The mechanical process becomes rather cumbersome. Okay, the second method is a little interesting. So, where we start by the assumption that the system is in the controllable canonical form, right. So, which means that that's all the coefficients just show up here. B has only one entry at the end, and they are just each other row has just once. Okay, simple substitution would show that A minus Bk, so k is of this form. So, minus kx will be of the form minus k1, k2, kn, x1 till xn. So, this will simply add up here. So, all the unknowns will just add up here. Of course, these are known, these are the unknowns. Okay. If the mu's are the desired pole locations and the desired characteristic equation, so these are known. So, these mu's are the locations where I want the closed loop poles to be, and I can expand this into this form. Okay. So, because the mu's are known, the alphas are also known. Okay. Just like here, right. So, I knew the mu's, they were like minus 1, minus 2, minus 2, and because of that these alphas were known. So, these are the alpha i's, each of those. Okay. So, the characteristic polynomial will now lead to a closed loop system. So, if I just look at how my system starts from the transfer function and the characteristic equation. So, these are nothing but the poles, but the alphas, the coefficients of the closed loop system, coefficients of the characteristic equation of the closed loop system, right. Okay, maybe on the reverse order, alpha n minus 1 and so on. Okay. So, what sits here are these alpha n's. Okay. So, what do I know? I know minus all these alpha n's. Now, equate with the unknowns. Unknowns are this a0 plus k1. So, at each step I have this one, that a0 plus k1 is alpha n, which means k1 is alpha n minus a0. So, both of these are known. These are known. So, a0 comes from the open loop, an comes from the desired poles, and from the desired poles I just write down the characteristic equation, and these are the coefficients of the characteristic equation. Okay. So, we will just write down in the just look at a quick example. I start with the characteristic equation. Again, I am just interested in the pole. So, in the state space, this will translate to A2 being 5, A1 being 8, and A2 being 4. These are my known quantities. Okay, and this sit in the state space in the last row of my A matrix in the controllable canonical form. Okay, now suppose I want to place poles at minus 1, minus 2, minus 3. The characteristic equation becomes SQ plus 6x square plus L11S plus 8. So, again look at how my closed loop will look like. So, here this is my alpha 2, this is my alpha 1, this is my alpha naught. Okay. So, now this is simple, right. So, how do I find the case? So, I know once I know the alpha n's, I know the a's, I am easily able to find the k, right. So, the desired state feedback controller therefore is with the k1 is 2, k2 is 3, and k3 is equal to 1, right. So, this kind of gets nicer when the system is in the controllable canonical form. The question that one may ask is, what if the system is not in the controllable canonical form, right. But what we know is that a system x dot equal to ax plus bu. Suppose I define a transformation x equal to pz such that z dot is p inverse of x dot. This is p inverse, x dot is ax, x is p times z plus P inverse B U. Okay. Now, what we know is that A and P inverse AP are similar, that the eigenvalues of A are the same as eigenvalues of P inverse AP. Okay. So, this similarity transformation, it preserves all the properties of the system. Now, if this is not in the controllable canonical form, can I find a P such that in the z coordinates P inverse AP is in the controllable canonical form? Okay. Now, assume that this is in the controllable canonical form, that I have z dot is, let me call this quantity as Az times z, let me also call this as Bz times U. Okay. Now, the poles here are the same. So, if mu 1 till mu n are desired pole locations for A in the x coordinates, they will be the same here. Mu 1 till mu n will be the desired pole locations for S for Az also. Okay, now I do the standard recipe. Az is in the controllable canonical form. So, U will be minus k times x, sorry, here it will not be x, but it will be z. Okay. So, I design the control law, I find a k of the form U equal to minus kz, and so this is in the z coordinates. What happens, or how does this U look like in x, which is the original system? Okay, let us quickly check, right. So, the system, okay, of course, we look at system which is fully controllable, and in this case, so what happens is that I design a control law U equal to minus k or k z kz times z. What is this kz times z? This is simply U equal to minus k. How will I write it in, how will I write this in x? So, U in the x coordinates is minus kx, in the z coordinates will be minus k p z, and this k times p I will call this as kz. Okay. Now, from this, okay, this is my control law in the z coordinates. So, what is, but my original system is I have to give the control to this system, right, not here. This is mathematically convenient for me to analyze, but eventually I have to control this this system. So, so once I have kz, what is the control law in z? What is the k? Okay, so let me call this as kz here. Okay, so this is nice. Once I get, so compute kz using the procedure stated in method 2. Now, once kz is obtained, now look at things here. Okay, once kz is obtained, I am just here, right. So, here till here and here. So, take minus kz, this is my kz, right. From here kz is k times b, sorry, k times p. Now, if I take this kz, which is equal to k times p, I do a p inverse, what I get is k. So, k is simply kz times p inverse. Okay, so let's redo everything now. Okay, first is, what is the p? Okay. So, if it is not in a controllable canonical form, I need to define a transformation which will take from A till Az, in which Az is in the controllable canonical form. Who takes this from A to Az? That is this transformation matrix P. How is this defined? Of course, I will not do the derivation of this, but let us say P is defined in this way. P is C, where C is the controllability matrix, C is the matrix B, A, B, A, n minus 1 B. Okay. Now, if I construct a P which is C times W, it will take my system from the standard form, from the general whatever given form to a controllable canonical form. Okay. Now, once my system is in the controllable canonical form, okay, and of course, because C is full rank, this P will always be invertible, right. So, that is so we do not need to worry about is P invertible. Okay. Now, first then I write this in the controllable canonical form and then design a control law Kz for this u equal to minus Kz. So, step 1 is compute Kz using the standard procedure, which was assumed that the system is in the controllable canonical form. Now, how does the Kz translate to the K for the original system? I just do the Kz times P inverse. Okay. This also proves that this is a sufficient condition, that if my system is in the controllable canonical form, then I can do arbitrary pole placements, which is sufficient condition, right. So, if I start with controllable canonical form, then it means that the system I can conduct pole placement, okay, which is just sufficient. Earlier in the lecture, we inferred that this is also necessary condition, and therefore, the necessary and sufficient condition for arbitrary pole placement is that the system is completely state controllable. I can not do a formal mathematical proof, but via these two conditions, it is easy to see why that is, why we say that a necessary and sufficient condition for complete state controllability is that the system must be completely state the necessary and sufficient condition for a complete pole placement or arbitrary pole placement of all the poles is that the system be fully state controllable. Okay, so are there any more methods? Of course, in MATLAB we can do several of this by just some one line command, but let us see what we can do. What do these things mean? Okay, so I will do this formula called the Ackermann's formula. Of course, I mean in most cases we can do all of these by just using a small command in MATLAB, but it is kind of it's good to know how things evolved into some nice computational tools. Okay, so this we will call as the Ackermann formula for pole placement. Okay, so what does this say? I start with a system x dot is Ax plus b times u, and I want to design u equal to minus Kx such that the closed loop poles are at mu 1 till mu n. So, that is the standard pole placement problem. So, this is the standard pole placement problem. Which is find k such that the closed loop poles are at these desired locations. Okay, now x dot equal to Ax plus Bu, u equal to minus Kx results in x dot is A minus Bk times x. So, what is the closed loop characteristic equation? Okay, so the closed loop characteristic equation will just be Si minus A minus Bk, and I will call this as A tilde Si minus A tilde. So, this where should I want this to be? This should be at S minus mu1. So, the closed loop poles should be from mu1 till mu n. I can write this as S power n plus alpha 1 S n minus 1 all the way till alpha 1, it will be here, sorry, alpha n minus 1 S1 plus alpha n. So, this should be 0. On the right hand side, things are known. On the left hand side, k is the unknown. Okay, so this is good. So, I will briefly mention what is called the Cayley-Hamilton theorem, which says that the given matrix A satisfies its own characteristic equation, which means that phi of A tilde is A tilde power n plus alpha 1 A tilde n minus 1 all the way till alpha n times I equal to 0. Right, what is the standard characteristic equation? We are just looking for lambda n plus alpha 1 lambda n minus 1 and so on. Okay, this is the standard characteristic equation, right. So, to take out the lambda, put in A, it will still satisfy the its own characteristic equation. Okay, so let us come back to the problem at hand, right. So, and then for simplicity, I assume that n equal to 3, even though the formula that we will derive at the end is valid for all n. Okay, so okay, just take the identity 3 cross 3 identity, then I have A tilde is A minus bk. So, these are all the terms in my characteristic equation. A tilde square will now be A minus bk square. So, this will be A square minus A bk minus bk A tilde. Okay, I am just writing down terms with so maybe skipping one small trivial step in the middle. A cube, this will be A minus bk whole cube. This will be A cube minus A square bk minus A bk A tilde minus bk A tilde square. Okay, so just believe me that this is true. If not, you can just work it out by yourself. So, what I do is I multiply the first term by alpha 3, then second term by alpha 2, third term by alpha 1, fourth term by alpha naught, and just add all of these 3. So, where will I be now? So, I will have alpha 3 I plus alpha 2 A in the tilde thing. So, alpha 1 A tilde square alpha 0 A tilde cube. So, this is the characteristic equation of A tilde, right, that it will satisfy its own characteristic equation. This will be 0. On the right hand side, now I have I A square A cube. This is I plus A, again I have to multiply all these things, right, alpha 3, alpha 2, alpha 1 A square plus alpha naught A cube plus a bunch of other terms. So, that will be alpha 2 alpha 2 goes here. So, this will be alpha 2 will be alpha 2 bk minus alpha 1 a bk. So, I am here now minus alpha 1 bk a tilde minus okay. So, okay, I think this should be 1 for the to be satisfying the characteristic equation, right. So, this will just go away, then okay, this also will go away. So, I am just left with all the terms on the on this term. So, that will be minus a square bk minus a b k a tilde minus b k a tilde square. So, this quantity here is now the phi of a. So, I can rearrange terms to now write phi of a as b. Now, take all the terms which have just b in it, b, b and b. So, this will be alpha 2 k plus alpha 1 alpha 1 will have terms of k a tilde, and then I will have one term corresponding to k a tilde square, that is this one. Then I will have another term corresponding to ab. So, that is alpha 1 k and k a tilde. These are the terms corresponding to ab, and lastly I will have terms corresponding to a square b, which is just k. Okay, so something nice seems to be happening here. So, okay, so what I have b, ab, a square b. This looks very familiar to what was happening in my controllability matrix. So, again on the left hand side I have phi of a is b, ab, a square b. This is my c, and the terms here, this will be alpha 1 k plus alpha 2 k, alpha 1 k a tilde plus k a tilde square. Then I will have alpha 1 k plus k a tilde, and lastly I will have k. Okay, the c is invertible, so let me just call this as m, right. So, I will have c inverse phi times a as some m, right, whatever that could be, some matrix m. Now, if I left multiply c with 0, 0, 1, so this guy goes here now, right. So, this matrix is remaining. Take this m and multiply to the left by 0, 0, 1, first term, second term and 1. So, this will just be, if I left multiply 0, 0, 1 with m, I am just left with k. So, through the Ackermann's formula, I can find k as 0, 0, 1, inverse of the controllability matrix and phi of a. Okay. Please note that phi of a is not equal to 0, right. So, phi of a tilde is equal to 0. Okay. Now, in general, I will have k as 0, just the last entry being 1, C inverse phi of A. So, this is the general version of Ackermann's formula for arbitrary pole placement. Okay. So, that is all. So, we start with A minus Bk with a characteristic equation. I have all these alphas which come as a result of expanding Si minus A tilde. I invoke the Cayley-Hamilton theorem, and therefore, you see, right. So, phi of A tilde is 0 and phi of A is not 0, because these coefficients correspond to A tilde. Okay. So, all the steps are detailed here, and this is how we compute the general formula for the Ackermann's formula. Okay. And again, some quick examples for you to quickly check. This is fairly mechanical. The first thing is just check if the system is controllable or not. Then you can use each of those methods to compare, and the system is already in the it's not in the controllable canonical form. So, you may convert it into the controllable canonical form to get the appropriate answer. And lastly, also look at solving it by the Ackermann's formula. And simple command in MATLAB can tell you this. Okay, so let's okay. So, the system by itself is in the controllable canonical form, right. So, the first method we just use the comparing of the coefficients of two polynomials. Method 2, system is in controllable canonical form, straightforward, and method 3 is the Ackermann's formula. Okay. And you can just check the system response. Again, I am not deliberately plotting this because it is just a matter of validation. We all know that all the states will go to asymptotically to 0. Okay. So far we were looking at A minus Bk x dot equal to A minus Bkx. If the system was stable, all the x will go to 0. So, x at infinity, everything goes to 0. Okay, that may not be all the time of interest, because our control architecture had a reference signal, a controller, a plant, output which was compared with the reference, resulting in an error, and such that the y had to track r asymptotically. Right, those were the standard tracking problems. Right, I want to track a step, track a ramp, or track a 10 units of a step, and so on. How do we translate that into problems of pole placement, right? So, those are called servo problems. A servo system is a closed loop system designed to precisely control the position, speed, torque of an actuator, such as it could be a motor, hydraulic system, or any kind of a robotic system. So, these are used in applications where precise motion control is needed, in aerospace application, robotics applications, surgical robots, and so on. Okay. So, we consider here a type 1 servo system, like a plant x dot equal to Ax plus Bu, y equal to Cx, and assume that y is equal to x1. So, type 1, so I will have a the plant will have a integrator. Okay, also mentioned here. Okay, and the problem now is, okay, this plant is now in the form x dot equal to Ax plus Bu, and I am designing a control law such that u equal to minus kx plus the reference signal. So, this is the input to the plant, right? It also has the reference component. So, u equal to, I can just write the u equal to minus kx plus r expanded in this way. Okay. So, I am now looking at x dot equal to A minus Bkx. This is the standard pole placement form, closed loop form, and I have something extra. where at steady state I want my output to track the some kind of a reference. At the steady state, the same system so behaves in the following way. X infinity, x dot at infinity is a minus b k x equal to infinity, and the reference signal at infinity, it does not change whatever. And this implies that if I look at this, so r at infinity will be in general any r of t, because it's a given signal, maybe a unit step or something like that. So so this one does not change. So I just do x dot, I take x infinity dot, I just take the difference and I get something like this. Right. So here I have, if I call this term as E, and I call this if I call this term as E, this term becomes E dot, and all I have is something very familiar looking system, right. So the design of a type 1 servo system, where my system had to track a reference R, is converted to a design of a general stability problem or a regulator system, where Et approaches 0 for any given initial condition E naught. So as long as A minus Bk is stable, and we have been doing this for a while now. So given a, even if it is unstable, I can design a B to make it stable. Not just make it stable, I can place the pole such that some desired transient and transient specifications are satisfied. Okay, now what is the x at steady state because of this? What is the u at steady state? Okay, I go back to my original equation. X dot at steady state, there will be, at steady state means things will, so there will be no transients, so x dot will be 0, a minus bk x infinity times this r. Okay, so I can just write down, so because the system is controllable and a minus bk all has non-zero poles, this is invertible. So I can write x infinity just from here, x infinity as so a negative here, a minus bk1 times r. So these are known, this I can design for it to be stable and so on. Similarly, u at infinity, this is interesting, is minus k at infinity plus k1 at r. So this goes to 0, right? We can check from here, right? So u at infinity is negative of the k of x and k1 at r. At steady state, y will become x1, and therefore the u will also go to 0. Okay, a simple example here, type 1 servo system. I have a pole at the origin. The desired closed loop poles can be arbitrarily placed somewhere. Reference is a unit step, and I can just do the entire math. The unknowns here are the k1, k2 and k3. The system is, I can write it down in the controllable canonical form. I can place the poles at desired locations, and I see that okay, it's just the simple math here. I can see that my system tracks a unit step very beautifully. Okay, so things that we have done so far is how to place the poles at arbitrary locations, and second, how to even solve some kind of tracking problems, right. So the takeaway here is, for the system, for arbitrary pole placement, the system needs to be fully controllable. Same thing also holds for tracking problems, and we had seen 3 methods of how to achieve how to solve the given pole placement problem. Thanks for watching. Next time we will ask ourselves few more questions of what if, so when I say u equal to minus kx, I assume that x is given to me. It may not always be the case. What happens in the case when x is not always measured or given to me? We will see that in the upcoming lectures. Thanks for watching.